That's right. And I think it's actually quite complementary because maybe two things here. I will talk about the emergence of grounded spatial language, so I'll focus a lot on actual agents interacting in some environment, which I think is complementary to what Tao was talking about. And then I'm adding another domain, which is spatial language, and it's one of the domains that I think has it's sort of the breadth of experiments that have been done in this domain, based on a particular data set that we collected, has been quite wide. Okay, so I'm going to focus on what is called locative spatial language. So there are phrases of the kind like the block left of the box from my perspective. So there's a spatial relation here. There's some landmark, the box, which is in relation to the spatial relation. And then there's also a perspective marker here. And all those things together essentially encode a particular conceptualization of reality. So if you're the listener to a phrase like this and you're asked to identify an object, then basically what you need to do is actually compute reference, compute the landmark, compute the kind of combination, the particular combination of constituents in order to arrive at some sort of referential reference. And as Luc mentioned, we are very much interested not only in the evolution of syntax, but also in the emergence of complex conceptualization strategies or semantics. And in this case, of course, they would be spatial. And what I'm showing here is a kind of the computational meaning of a phrase like this, which is actually sort of combining all the things that I just said, which is constructing regions, spatial regions. So if left of the box from your perspective is actually kind of region in space that can be used to identify objects, combining also with other categories such as block, which is mentioned here, and also combining in the lower part of this network the perspective computation, which is kind of a way of taking a phrase like from your perspective and manipulating the way that the agent conceptualizes reality. And so we're interested in both the evolution of the syntactic structure of phrases like this, but also in the evolution of the semantic structure. Now, as maybe some of you know, spatial language, even though it's kind of perceptually very central for us, it's maybe also evolutionary very central for us, it's not universal. So projective categories like front, back, left, and right exist in English, but also Japanese, but they don't exist in all languages. So this is Manam. It's an island off the coast of Papua New Guinea, which has a very large volcano in the middle. And instead of using these projective categories, these people have developed a system that's completely based on the direction towards the volcano. So they would say things like, he went in an inland direction rather than saying something like, it's in front of me or back or right of me. And so one of the key issues then is to develop models, agent-based models that can account for the emergence of projective language, spatial language, but also, for instance, of absolute spatial categories. And in some cases, also the combination of such strategies, such as, for instance, in English, we do have absolute spatial categories, such as north, east, south, and west. Okay. And so I said that we're interested in grounded language, so we're particularly interested in experiments like this one, where two agents interact in a particular environment. These are two agents from a larger population of robots, actually typically around 25. And what's happening here is that they're discussing, or one of the agents is trying to draw attention to an object in the environment. It's actually the agent, sorry, there's no sound. I can try sound, but, well, oops. Okay, I'll go back here for a second. So this is the phrase that's going to be uttered. It's going to be uttered by this agent in the front here. Both of them are scanning the environment first. They see this object for the first time. And then he picks a goal. He wants to talk about one of the objects in the environment. And this is already at the later stage of the experiment where they have spatial categories and also landmarks and perspective. In fact, in some sense, the structure of this sentence is very similar to the English sentence. Now, he doesn't know what that refers to, so he signals that he doesn't understand that, and then he gets a pointing action from the speaker in order to identify the referent, in order to give the agent, which is in this case the learner agent here, in this particular interaction, a chance at understanding the meaning and maybe understanding the referent and potentially becoming better at pointing to this object in the future. Okay, so this is actually the same interaction, but I want to stress the grounded aspect here. So this is something that Luc also talked about. So it's important here that each of these agents have their own perspective on the scene, using their own camera images. They're scanning the world. They're actually building these kind of a little bit more abstract representations of this of the environment. This is the environment that he estimates he's in, and this is the environment that he estimates he's in. And so you already see that, as you can see, the yellow things is the yellow blocks, and then this blue thing here is this box here, and then that thing is the kind of what can be used as an absolute marker. And you may already see that this actually has actual consequences on the kind of world models that these agents build. In fact, the world model that this agent builds is essentially very different from the world model that he builds. I mean, it's rotated for once, but there are also, especially working with robots, there are sort of estimation errors. So that object there, he actually puts it at the corner of this this box object, whereas he actually sees it more to the well, depends on how you call it, but it's actually sort of the left of it. And so this is, of course, one of the issues that language has to solve, is that we are all looking at scenes from our own perspectives, and that we may make different sort of estimations of what the world looks like, especially in terms of actual numbers, and for instance, in terms of distance and rotation of objects that we're estimating. So it's, of course, important because this is one of the problems that language actually solves. So just to kind of reiterate on this, if we use robot agents and each agent has its own perspective on the scene, they all have their own history of interactions with the world and others, and of course internal states are not accessible to other agents. So that's also something that Luc mentioned already. And I'd like to stress a little bit sort of the general structure of these experiments, agent-based models with robots, is that there is a sensory motor system which establishes some sort of initial perception of the world, some stable perception of the world, which can then be used in these to conceptualize reality in various ways. For instance, if I want to talk about an object, choosing the right conceptualization of that object in order to discriminate it versus other objects in the context, then obviously there's this area of how these meanings get translated into actual utterances, which is more related then to the emergence of syntax. And the hearer has to go through these steps in a sort of reverse order, trying to extract as much meanings from the sentence that he can understand. Then use it to interpret in the world in order to arrive at the action that he has to take. Okay, I showed one example of a scene like this, of an interaction like this. I should stress that we built a very large data set of spatial scenes like this, so more than 1,200 scenes, each of them consisting of sort of perceptions of one and basically two agents. That could be speaker and hearer. They have different perspectives, so in some cases the arrows are the estimation of robot positions. In some cases they can be looking at each other sort of directly face to face. In other situations there's a little bit more, the perspective is much closer to each other. And of course we can also manipulate various aspects of such scenes, data sets, such as the existence of projective landmarks, such as the box, and also the existence of, for instance, absolute markers. If you remember back into this video I showed, there's a very large marker on the wall, which is maybe something like the volcano, that can be used to trigger the emergence of absolute spatial systems, as, for instance, in the case of mana. It's not just data sets that are important, but it's also measures. If you think about benchmarks, and Luc already mentioned some, such as communicative success, and also whether there is alignment, for instance, between the speaker and the hearer, but also more globally speaking on the population level. And then also maybe there are so measures that are related to the reuse of symbols and the compositionality of symbols, if you're interested in the emergence of syntax and semantics, of course. Data sets like this have been used for studying relatively a wide variety of questions. And I'll particularly focus here on the last four. So very briefly, of course, because in the interest of time. The first being, how can spatial categories form? So, lexical sort of type experiments. So how can spatial categories form in populations of agents? Then maybe the next step would be a question about maybe some of those compositional strategies. So for instance, how does landmarking evolve in a population of agents? So spatial landmarking. And then also, what is the function of grammar and how can grammar emerge in populations of agents? And I'll have basically one slide for each of those to give you a sense of how these experiments are going. Now, I should stress that all of those are using exactly the same data set and relatively similar measures. So the first set of experiments that we did is the emergence of lexical languages. So here, basically, agents are allowed to use single-word utterances, in some cases multi-word utterances, but basically single-word utterances in order to refer to objects in this particular spatial environment. And this is a graph that shows some of the dynamics, and Luc already explained a little bit what we might be interested in. So the green line would be, for instance, communicative success, which goes up, meaning that these 25 agents over time developing a lexical language are able to solve that problem in this particular data set. Here's an example of what these spatial categories might look like. Here's actually a constrained example, so they're only developing absolute spatial categories. And you can see that, in this case, they have 4 words with particular meanings attached, and they're slightly different across agents because they don't have access to the internal states. But if you actually check, they're sufficiently similar across the agents in order to allow for the agents to be successful in this communicative task. Now, one of the things that we like to do then is, of course, to manipulate some of those features of the environment. And this is a result from experiments where we manipulate the existence of absolute markers in the environment versus the existence of projective landmarks. And essentially, what happens is that in this condition, the projective landmarks are always visible and there are no absolute markers. And what that graph means is that in this case, the mechanisms actually work to develop a system that is only based on this projective system, on this projective landmarks. Whereas this is an example here where there's only an absolute marker available, and again, the same mechanisms give rise to an absolute system, which means essentially that the mechanism is flexible enough to account for the emergence of both absolute terms, but also these intrinsic projective terms. Of course, it's interesting also to look at mixed cases. So this is a case where we manipulate the environment again in 2 particular ways. So on the one hand, these agents are in an environment where there is a projective landmark, but the objects that they're talking about are very distributed in terms of the angular distribution, whereas in this environment, they are distributed much more along distance terms. And so if you look at this graph, then basically what it tells you is that in cases like this, the agents actually do develop more angular terms, so more things like front, back, left, and right. Whereas in cases like this, they would use more proximal terms such as near and far. And then obviously, interestingly, also would be a combined condition where both of those types of data exist in the data set. And you can see that they actually find another equilibrium where it's not just an addition of angular terms and projective terms, but sort of some combination. Okay, we then moved on to look at compositional semantics and in particularly landmarking. So this is an experiment where agents not only allowed to use single word utterances such as left, but where we actually look at also compositional strategies, including marking the landmark. So left of me or left of the box, for instance. And again, it's very helpful to have these data sets because we can manipulate exactly the distribution of objects and existence of objects and the number of objects in the environment. And basically, long story short here, what the story is that if you are in a simple environment where you're always facing with your interlocutor and have the same perspective, then it's perfectly fine to have an egocentric strategy where it's front, back, left, and right. But if you are in a world where there are many objects and your perspectives are varied, then it actually makes sense to have a complete system where you're allowed to use landmarks, such as left of the box, left of me, and you're also marking it explicitly. So the listener doesn't have to infer too much by not marking it. And then we can use this also to drive language evolution experiments where we show that agents can actually go from egocentric systems to systems that are much more compositional and, for instance, include landmarks. Lastly, emergence of spatial grammar, which is a little bit of a similar point, essentially. So if you look at just the lexical material, such as link, block, there, so determiner, links, and left and block, then, for instance, in German, you can build a variety of phrases, such as the left block, or left of the block, or the block to the left, which, well, in English they don't, unfortunately there's a to in English, so in German it actually works. The lexical material is the same, and it's sort of the grammatical relation that tells you the different conceptualization strategy that's used in these particular phrases. So, for instance, in an adjectival phrase, what you actually have to do is what is called a group-based spatial reference strategy, which you see up there, which is you have to do some particular manipulation and you have to imagine an object in the middle of these objects and then apply all the spatial reference systems you have. So again, we can look at actually how important this is. So this is an experiment where we, again, manipulate the environment. And the story here is a little bit similar to the one in the compositional semantics. If you are in an environment where you're looking at the same, at the scene from the same perspective, with relatively few objects, essentially you get away with a lexical language, but the more complex the environment gets, the more important the grammatical relations become in order to mark the different conceptualization strategies available in the language. And again, this is a very nice evolutionary story where we can show that, you know, when we slowly change the environment from something which is less complex to something complex, then this also may drive actually the evolution of, for instance, grammatical markers in the population because they are necessary in order to solve the communicative task. How much time do you have?
1 minute.
What? Seriously?
No, 5.
Okay.
About 10.
So the bigger picture again, so this is the same data set, but manipulating the complexity of the environment, we can essentially show that, you know, simple lexical languages can emerge first. And then if we increase the complexity of the environment, we can see sort of first compositional semantics emerging, and then also full grammatical strategies. So just to go back to this point, what's important here is maybe the open-endedness of the environment. There's no central coordinator, so it's a decentralized evolutionary system in a sort of complex system. And then there's no telepathy between the agents and no direct access. So then, yeah, so if you're interested in more detail, there's actually a book that's freely available that goes through all these experiments. Let me sort of make a few points of why this may be important to do agent-based models in general or even use robots. And the obvious first point is maybe if you're interested in grounding, which I think from an AI perspective, from an artificial intelligence perspective, is one of the key problems, how do symbols get grounded in the real world, then it's obvious why you want to have a setup like that allows you to study that directly. But from the viewpoint of maybe language evolution, I think there are a few other points here that I would like to quickly go through that show why this is important. And the first one is increased realism, the second one is robust models, and the third one is rich semantics, and then also the body itself as a driving force for language evolution. The first one is increased realism, and this basically pertains to something like this. So when Luc started in 1996 to do the first language evolution experiments using agent-based models, he was basically learning in some sort of abstract symbol space, mapping words to this abstract symbol space, so objects to words. When we actually later extended this to work on grounded data sets, this is about naming, we actually found that this is absolutely not sufficient because really this already presupposes kind of a structural discretization of the space that you don't actually have if you work with real robots, because basically all the data that comes from vision is essentially continuum. And so we had to develop a much more complex model in order to account for this. This is actually the same experiment, but using grounded data. What you see here on the left are these kind of experiences that the robot has, which are kind of objects, but in the continuous color space, in the continuous spatial space, in the continuous feature space, essentially. And so the model is actually much more complex, these are the words that are mapped to these particular prototypes. So you need to have a prototype representation and so on and so forth. And this is something that actually grounding kind of forces you to develop. The second point I would like to make about why grounded models is about robustness. And it's a little bit related to the point that I made earlier, that both of those agents have different perspectives on the scene and you see the scene from different viewpoints. But not only that, they also use their own sensory motor apparatus to establish things like distance and what color values they would attribute to these objects in actual continuous terms. And there's actually a lot of error that comes in through those systems. And what I'm showing here is actually if you manipulate the distance of the object, what is the estimation error the further away the object is in space? And obviously, we have the same problem because we are not actually sharing the continuous features of the distance that we see objects in or the colors that we see objects in. And so that's something that language actually helps to overcome, is this kind of difference in perception and the errors that come with that. The third point of why grounded models are important is maybe something like rich semantics. What I'm showing here is kind of different ways of conceptualizing the same topic or the same referent, this object here, in English. And these are all different ways of conceptualizing that object in English. For instance, you can say the block in front of the box from my perspective. You can say the block left of me, the block near the box, and so on and so forth. And this kind of rich semantics you only get if you actually have a sort of an additional layer, which is kind of the world model, the semantic layer, and the syntactic layer. And lastly, if you're interested in the body as a driving force for language evolution, here's an example that I like very much from Martin Lemmens, who has studied posture verbs in Dutch. And it actually turns out that posture verbs in Dutch are a very reproductive system for metaphorical extensions. And so of course, there's an evolutionary trajectory here that initially they start out meaning only the bodily postures, but then over time they get extended to objects in the environment, and at the very end actually also to things like much more metaphorical use, such as we are sitting in an economic depression, which is something you can say in Dutch, but that uses sitting in a particular way coming from actually initially from the body posture. So if you're interested in this kind of experiment and you want to study this using agent-based models, then having a body is a kind of prerequisite. Okay, so then why benchmarks? Last slide. Last one. So first of all, what is a benchmark? In my mind, this is essentially much related to notions of benchmarks in, let's say, artificial intelligence and machine learning. They're essentially a data set or a particular simulation bundled together with a set of evaluation criteria. So in our case, maybe communicative success, the reuse of lexical material, and a set of example results that kind of anchor a particular investigation and show that, okay, given this data set and those particular evaluation criteria, I can achieve this kind of performance results. And it's then up to the community to take that up and potentially provide other mechanisms and additional algorithms in order to show what could be potential algorithms for solving exactly the same task. And I really like this idea of benchmarks because they kind of bundle a particular task and its evaluation. They make it available for the community, but they also essentially clearly define the boundaries of the model because you're sort of constraining the thing that you're interested in a particular way that then allows to compare different algorithms and systems. And the consequence of this is, of course, that there's an increase in repeatability, so you can actually kind of share results in the community. And of course, there's also increased measurability and comparability, so you're able to benchmark algorithms with respect to this particular set of data set, evaluation criteria, and example results. And to some extent also, which I think is interesting maybe for the progress of this whole endeavor, is it sort of shifts the discussion from some particular mechanism and particular algorithms to the discussion of the environment and the mechanism, so together. Because you're achieving a particular result, a particular numerical result in a particular environment. And I think that's in general kind of helpful to understand also the landscape that's existing in agent-based models. Thanks very much.